Good morning, chemistry nerds. We're going to do a screencast on quantum numbers. So I'm going to start off by showing you a slide of notes that we took in class. If you remember, Bohr discovered that the electron couldn't reside at just any location within an atom's electron cloud, but could only stay at certain places associated with particular energy values. Later work by Schrödinger developed an equation to describe these locations, and we're going to look at not the equation but the four numbers that are the solutions to the equation, and they are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So there are a few things that you need to know about each of these numbers because they describe unique things about where the electron is. So starting off with the principal quantum number, that's telling us the electron's distance from the nucleus. Some other things that you need to know about it is its symbol is N. It can have a value of any whole number, and it's often also known as shell. The angular momentum quantum number tells us the shape of the orbitals within the shells. So some shells can have more than one sublevel within them, and each of those sublevels are going to have a different shape. Its symbol is a cursive L, and it can have values from 0 to n-1. We just refer to this as sublevels because it's describing the shape of these sublevels. You need to know that the L values that are required to describe the elements currently on the periodic table are 0 through 3, and we have letter designations for each of those sublevel shapes. S is a spherical shape, P is a propeller shape. I'll do the best I can to draw with my crude stylus here. So that's sort of the three-dimensional shape of a P sublevel. A L value of 2 corresponds to the letter designation for D, and it sort of looks like two P sublevels superimposed on each other in kind of this cross shape. My mnemonic device, since it's D, is to think, well, that kind of looks like a flower, so daisy. And an L value corresponding to 3 is known as the F designation, and that's a four-dimensional shape, so I'm not going to really draw any pictures for that. It would just get way too hard. The magnetic quantum number tells us the orientation of each of these sublevels in 3D space. So there are different ways that you can turn each of these shapes in space, and each of those corresponds to a particular place that electrons can reside, and we call those orbitals. Its symbol is M, and its values are everything from negative L to positive L, including 0. Each value that you have here represents a different way that that orbital can be turned in space where electrons can occupy it, and 2 electrons for each orbital, 1 in each spin state, which gets us to the last quantum number. It's the magnetic spin of the electron. Sort of think of it like North Pole and South Pole for an electron. So for every one of these orientations that you have here, you can put 2 electrons in it, 1 with a positive spin and 1 with a negative spin. And just some other equations. N squared is equal to the number of orbitals in a shell, and since you can put up to 2 electrons in each orbital, the maximum number of electrons in a shell is twice the number of orbitals. So we're going to make kind of a matrix solution for all of these, and that's what I'm going to show you on the next slide. So here's kind of a table that shows the matrix solutions for these, and I also included a version of the periodic table showing how all of these quantum numbers fit together to produce the shape of the periodic table. So if we start off with the principal quantum number, it can have any whole number value, so its lowest value is 1, which means if I follow the equation for angular momentum quantum number 0 to n-1, well, 1 minus 1 is 0, so the only value for L that we can have in the first shell is 0. And if you recall on the previous slide, 0 corresponds to an S-shaped sublevel, and the magnetic quantum number can have values negative L to positive L. So negative 0 to positive 0 is just 0. So I have one value for the magnetic quantum number, so that means one orbital, and I can put 2 electrons in that sublevel since there's only one orbital, one spin up, one spin down. So one orbital, 2 electrons in it, and that's the total for that. And this explains why the first row on the periodic table only contains 2 elements, because it only has enough space to put 2 electrons. Moving on to the second principal quantum number, now I have 2 possible values for the angular quantum number, because it's going to be 0 to 2 minus 1, so it's 0 and 1. We already discussed that 0 corresponds to an S sublevel, and there's only one M value for 0. Negative 0 to 0 is just 0, and so 2 electrons there. But my P-shaped sublevel now can have values negative 1, 0, and 1, because we're going negative L to positive L. So that means 3 different orbitals in a P sublevel, put 2 electrons in each, means my P can hold 6, which is why this part of the periodic table here is 6 elements wide, because there's space in a P sublevel for 6 electrons. So the total number of orbitals in the second shell is 4, 1 S and 3 P's, and I can put 2 electrons in each for a total number of 8 in the second shell. Moving on to the third principal quantum number, that means my values for L can be 0 to 3 minus 1, so 0, 1, and 2. Again, we have an S with 1 orbital, a P with 3 orbitals, but now we have L equals to 2, which is D, and there are 5 different values for M, so 5 orbitals, negative 2, negative 1, 0, 1, and 2. So that means I can put 10 electrons in a D-shaped sublevel, which is why this part of the periodic table here is 10 elements wide. So my total orbitals in this shell are 9, 1 S, 3 P's, and 5 D's. I can put 2 in each for a total number of electrons in the third shell of 18. You might notice that the third part of the third shell, the D's, are actually here in the fourth row, and we'll cover that, why that is, in a second video. The fourth shell now has angular quantum numbers of 0 to 4 minus 1, so 0, 1, 2, and 3. And you've probably noticed here that these are sort of like Russian nesting dolls. Each shell has all the parts of the previous one, plus one new one. So we have an S with 1 orbital, a P with 3, a D with 5, and now we have an F, which has L values of negative 3 to 3. So that means 7 orbitals in an F sublevel. Put 2 in each, and the F can hold up to 14, which is why if you see down here, this skinny part on the bottom is 14 elements wide, because you can put 14 electrons into an F sublevel. My total number of orbitals are 16, 1, 3, 5, and 7, and putting 2 in each gets to 32. And you might also notice, similarly, like we didn't experience our first D, even though it's a 3D until the fourth row, F, even though it's part of the fourth shell, isn't encountered into the sixth row. And we'll talk about that in a later video. Sorry guys, lost my train of thought there for a second. So we're not going to continue on with principal quantum numbers 5, 6, or 7, even though there are 7 rows on the periodic tables, simply because, sort of like the D's and the F's, each get further and further behind the shell to get to the next L value, which would occur in the fifth shell, which would be an L value of 4, which corresponds to a shape of H. We wouldn't actually encounter that until the 8th row. So we don't have enough elements to encounter any sublevels higher than F. So you can see all the patterns that you need to explain the different parts on the periodic table just going through quantum number 4. So I hope this helps you guys see how these are put together. The things that you need to remember especially are the equations for the possible values of these quantum numbers, so that if I give you any one quantum number, you can use those rules to tell me the possible values for each one. And you also need to know what they stand in for, that the principal quantum number tells you the distance, the angular quantum number tells you the shape of the orbital, and the magnetic quantum number tells you the number of orbitals for every m value you have that's a unique orbital. All right, thanks guys, and we'll talk later.